Hello and welcome to Chemistry with Dr. Clark. In today's video, what I'd like to talk about is calculating Gibbs free energy and then using the value of that to decide if a reaction or a process is spontaneous. Now, in this video, we're going to use numbers and calculations to decide if something is spontaneous or not. If you are attempting to decide if a reaction is spontaneous or not, but you don't have any numbers given, so you don't have any of the enthalpy changes, you don't have any of the entropy changes, then I have a separate video that discusses how would you predict whether something is spontaneous if you don't have any of the numbers. Basically, you're deciding if the reaction is exothermic or endothermic, and you're deciding whether the entropy or disorder increases or decreases. So if you're looking for an explanation of how to predict spontaneity, spontaneous or not, without doing any calculations, you should probably pause this video and go and take a look at my other video that talks about deciding if a reaction is spontaneous or not. If you do have numbers, then you're in the right place. Because in this video, we will talk about if you know the values of the enthalpy change and the entropy change, you'll be able to calculate the Gibbs free energy and use that to decide if you're spontaneous or not. So let's first talk about what Gibbs free energy is. So Gibbs free energy is the maximum amount of reversible work that can be performed by a system as long as the temperature remains constant and the pressure remains constant. Okay, so it's the maximum amount of reversible work. The way we calculate it, delta G, the change in Gibbs free energy, is equal to delta H, the change in the enthalpy, minus the temperature, T, times delta S. And delta S is the change in the entropy. So if you know the enthalpy change, the entropy change, and the temperature, you're able to calculate Gibbs free energy. Okay, and I have all those things defined here. So my delta G is the change in Gibbs free energy. Delta H is the enthalpy change, delta S is the entropy change, and T is the temperature. Now, if you've done chemistry, you know that often in the same topic, there's a bunch of terms that are used that really sound the same and are very confusing. This would be one of those, right? Delta H is enthalpy change, delta S is entropy change. Okay, and you have to be really careful not to mix the two of them up, even though they sound really close and are used in the same calculation. Now, the other thing we need to talk about here is units. So the change in the Gibbs free energy is measured in kilojoules per mole, and sometimes just kilojoules, but usually kilojoules per mole. The enthalpy change is usually measured in kilojoules per mole, and again, sometimes the moles is dropped, so it's just kilojoules. The entropy change is a little different. It's measured in joules per Kelvin per mole. So the kelvins and the moles are both in the denominator of the unit. Because this is measured in kelvins as the temperature, when we do talk about temperature, it has to be measured in kelvins as well. You have to have consistency between your units, right? So if this has a kelvins in it, the temperature also has to be in kelvins. The other issue here is that the energy units don't match up, right? Gibbs free energy is in kilojoules. Enthalpy changes are going to be given in kilojoules, but the entropy changes are given in joules, right? These tend to be much, much smaller, so they tend to be given with much smaller numbers, right? So they're in joules rather than kilojoules. But if you want to be able to throw all of these numbers into the one calculation and make it work, they have to be consistent. So you're going to have to convert this from joules per Kelvin per mole into kilojoules per Kelvin per mole. And the way that you're going to do that is dividing by 1,000. Now I point that out because when you have tables of these numbers, the delta H's are always going to have kilojoules. The delta S's are always going to have joules, and if you want to put them in the same formula, you're going to have to convert the units. So you're going to have to turn your delta S from joules per Kelvin per mole into kilojoules per Kelvin per mole. Okay, it's just one of those things that's part of this problem that you have to remember. Now, if you're going to be talking spontaneous, and you do look back at the other video that I have about spontaneity, basically the delta H and the delta S are like an election where you get 2 votes. Okay, so you have an election, you're voting for something, and there are only 2 votes, delta H and delta S. If the delta H says yes to spontaneous, and the delta H says yes to spontaneous, then the reaction is going to be spontaneous. If the delta H says no to spontaneous, and the delta S also says no to spontaneous, then the reaction is not going to be spontaneous. The only problem that comes is when the 2 of them vote against each other. Let's say that your enthalpy change says, yes, this reaction should be spontaneous, but your delta S says, no, this reaction should not be spontaneous. Well, then who wins? You've got 1 vote for, and you've got 1 vote against. That's part of the reason why we want to do this calculation, because those situations are very hard to figure out unless you have some numbers to back you up. Now, the general rule of thumb is if you're at very low temperatures, the enthalpy becomes the more important one, right? Because in this equation here, if you have a very low T, very small t times this will be a very small term. So your delta H is going to be dominant. So at low temperatures, the delta H is the dominant vote. So if it votes for, then it's most likely going to be spontaneous. If it votes against, then most likely it's going to be non-spontaneous. But at high temperatures, you get the reverse. Because at high temperatures, this value of T is going to get really big. So if you've got a really big number times delta S, then this part of the equation is going to become the important piece. So if you're at high temperatures, the entropy change becomes more important. So if your delta S at high temperatures says spontaneous, then it's most likely spontaneous. If your delta S at high temperatures says no, this is not spontaneous, then it's probably not going to be spontaneous. Okay, because there's a temperature in here, right, it's going to affect which one of the 2 terms becomes the dominant term. And the problem that I have coming up will illustrate that. All right, so let's say that we do a problem. Okay, let's skip this for a moment. So in this problem here, I have given the delta H. So I told you that it was minus 15.2 kilojoules per mole. I've given you the delta S. I've told you that it's minus 173 joules per Kelvin per mole. You can see the mismatch of units. And then I've basically asked you to do the calculation twice. I want to know what happens at 10 degrees, and then I want to know what happens at 500 degrees. So at the low temperature, the delta H should be the dominant term. And at the high temperature, the delta S should be the dominant term. Okay, so I've got 1 at low temperature, 1 at high temperature. Now, if we do go back to what I skipped past, in order to decide if something is spontaneous or not, if the value of delta G that you calculate is negative, then the process is spontaneous. Now let's talk about the reason for that. If we rewrite our equation here, delta G equals delta H minus T delta S. If you go back to my previous video on spontaneity, I had said that exothermic reactions tend to be spontaneous. So if you're exothermic, then you tend to be spontaneous. Now, if you think back to when you talked about enthalpy changes and you did like heating and cooling curves and calorimetry and all those things, if you have an exothermic reaction, that's telling you that your delta H is negative. Right? Exothermic has a negative delta H. Minus. Now this temperature is on the Kelvin scale. The Kelvin scale does not have negatives. It starts at 0 Kelvin and it works its way up. So this temperature will always be a positive. We also said that if you increase the amount of disorder in the system, then that's a good thing. That's positive. So an increase in disorder is an increase in entropy. And if your entropy is going to go up, that means your delta S is going to be positive. Right? Your delta S, your disorder, is going to go up, so it's a positive thing, right? That's a positive change. So this would be positive. So if we take a look, this was a negative minus, what's a positive times a positive? A positive. And if you have a negative number and you subtract off a positive number, it's still going to be negative, right? Let's say this was a minus 3 and you're going to minus off a positive 4. If you subtract off a positive number, minus 3 minus 4 is going to be minus 7. So if you have a negative number and you're subtracting, that means it's going to get lower. And if you're subtracting off a negative number, a positive number, that's taking it down. So if you're exothermic, that's spontaneous. That's a vote for spontaneous. If you've increased the disorder, that's a vote for spontaneous. And both of these together will always give a negative value for your delta G. That's why negative delta G's are spontaneous. Let's say that we talk about the opposite. If exothermic is spontaneous, that means endothermic would be non-spontaneous. So if you are exothermic, that was a negative delta H. If you are endothermic, that's a positive delta H. Okay, increasing disorder was good. If you are decreasing disorder, that's bad. If you are decreasing disorder, you are decreasing entropy. So you had lots of entropy, and then you decreased it. The change is negative. So your delta S here would be negative. Okay, so instead of a positive here, you've got a negative. So your temperature is still positive because it's a Kelvin scale. It's always positive. So you have a positive number minus a positive number times a negative number. Okay, so maybe what we'll do is we'll just cover this up. So you've got a positive number minus a positive number times a negative number. What's a positive times a negative? That's a negative. So you got a positive number minus a negative number. And if you've got two negatives that come together, minus a minus is the same as adding a positive. So this would be plus plus a plus. So your answer is positive. So if you have two votes against, if you are endothermic, positive delta H, that's a vote against. If you've got a decrease in disorder, that's a vote against, that's a negative delta S, then putting these numbers in will give you a positive answer. Let's say we do put some numbers in. Let's say that my delta H was, say, 4 minus, and we said that this number here should be negative, so let's say negative 5. 4 minus a minus 5 is like saying 4 plus 5, right? The two signs cancel, which gives me a 9. So if your delta G is positive, then the process is going to be not spontaneous. So negative delta G is spontaneous, positive delta G is not spontaneous. And you are going to have to memorize that, right? It'll make your life so much easier if you can say, oh, my delta G is positive, that's not spontaneous. Or my delta G is negative, and therefore it is. And at the changeover, when do positive numbers change into negative numbers? At 0. If you're at 0, the whole thing is at equilibrium. Okay, so you've got an equilibrium rather than a spontaneous or not spontaneous reaction. Okay, now the reason why I wanted to talk about this is because in our problem, I'm not only going to ask you to calculate the value of delta G, but I'm then going to ask, is it spontaneous or is it not spontaneous, right? So you have to judge at the end. So let's talk about doing the problem. Now, I'm a big fan of writing down my formula. So if I'm going to be calculating delta G and I have a formula for that, then I am definitely going to write it down. So delta G equals delta H minus T delta S. And if I write my numbers off to the side, in order to do this, it involves delta G's, it involves delta H's, it involves T's, and it involves delta S. right? That's the fourth variables involved in this equation. So if we write down what we know, delta H is a minus 15.2 kilojoules per mole. Okay? If we write down our delta S is a minus 173 joules, kelvins, moles. And I can see right away that I've got kilojoules versus joules, right? You can't have two different units in the same problem. So what we're going to do is I am going to divide this by 1,000, and that'll turn joules into kilojoules. So if I do that, I get a minus 0.173 kilojoules per Kelvin per mole. Okay, I'm going to fix that problem right here. Now, what else did they tell me? They say, please calculate the value of delta G. So this is going to be my question mark. That's what I'm looking for. And my temperature is 10 Kelvin. That's pretty cold, right? That would be minus 263 degrees Celsius, right? It's ridiculously cold. But now that you have all your values, this is just a plug them in and work it out kind of problem, right? Don't know the delta G. Do know the delta H. That's a minus 15.2 kilojoules per mole. Minus the temperature, I know that. That's 10.0 kelvins. Times, and I really should put it here, but I ran out of room. So times the delta S, and I know that too. It's a minus 0.173 kilojoules per Kelvin mole. Whew. Ran out of room there a lot more than I had anticipated. Now, you could probably throw this whole thing in your calculator. Your calculator will take care of the whole thing for you. But I would like to work through it in steps just so that you can see how the units are going to work. Okay? So, the delta H is standing out here by itself. Then it's a minus, and then it's a multiplication, right? And you know that we have to do the multiplication first. So, let's leave the minus 15.2 kilojoules per mole here. Let's leave the minus, and let's do the multiplication. So if we haul out our trusty calculator, I'm going to have 10 times a 0.173 negative, which gives me a negative 1.73. Now, part of the reason why I wanted to show this calculation in pieces is so that we could talk about units. In the temperature, I have 10 kelvins. So there's a kelvins here. That's really in the numerator, right? Because this whole thing would be over 1. I also have a negative 0.173 kilojoules per Kelvin per mole. I've got a kelvins here that's in the denominator. If you've got a Kelvin in the numerator and a Kelvin in the denominator, they do cancel each other out. And what are you left with? Just kilojoules per mole. Right, so I will have kilojoules per mole, which is good because if you're going to add these two together or subtract them, if this one's in kilojoules per mole and this one's in kilojoules per mole, when you do the subtraction, your answer will be kilojoules per mole, and we want Gibbs free energy to be in kilojoules per mole. Now, you do have a minus, so they both become positive. So this is going to be a negative 15.2 plus 1.73. So 15.2 negative plus a 1.73 will give me a negative. Okay, so delta G is a negative 13.47 kilojoules per mole. This is kilojoules per mole, this is kilojoules per mole. You're adding them together, so the answer is in kilojoules per mole. Okay, now you can see how in the beginning we were saying that if you're at a very low temperature, this second term becomes pretty tiny and your first term becomes dominant. Well, just look right here at my calculation. This term was a minus 15.2. Now, I know it's negative, but 15.2 is a pretty big number. Just look at my second term. My second term is only 1.73. Right? 15.2 versus 1.73. This is a pretty small term. So the delta H here dominates. It's the most important part, right? This one was negative. Negative delta H is good. This was a negative delta S, right? Negative delta S means the disorder is dropping. That's bad. So I had one vote for spontaneous and one vote against spontaneous. Because this one was so big and this one was so small, this one dominates. The vote for outweighs the vote against. And I end up with a negative delta G. And we know from the earlier page that if delta G is negative, then this is spontaneous. Right? My delta H dominates at low temperatures. And a negative delta H is good. A negative delta S is bad. Vote for spontaneous versus a vote against. And at low temperatures, this is my star, right? Your delta H is the most important term. All right, so let's see what happens when we raise the temperature. So if we talk about the exact same problem, but we've just changed the temperature. Now, let's see if I can give myself some more room. Delta G equals delta H minus T delta S. I would still like to write out my variables, delta G, delta H, T, and delta S, but I will try and give myself a bit more room. This is one of the reasons why whoever teaches you a course will always say you should do the practice, do lots and lots of problems, because the more problems you do, the better you get at understanding how to do them, but also you get better at laying them out. So that way when you lay them out, they're easier to see what's happening, your spacing is better, right? It's just a lot nicer when you've practiced your problem a few times, right? It makes it easier for you to understand it, and it makes it easier for whoever's correcting it to understand it as well. Now, for this problem, I'm going to keep the same delta H. The delta H is still a minus 15.2 kilojoules per mole. I'm going to keep the same delta S, and I've already divided it by 1,000, so I'm going to keep that one. Minus 0.173 kilojoules per Kelvin mole. Kind of got squeezed there. The temperature, though, is different, right? The temperature this time is 500 Kelvin. Before it was 10, now it's 500. So this will be 500 kelvins. And again, I'm being asked to calculate the value of delta G. So it's the same set of numbers, right? The delta H is the same, the delta S is the same, but the temperature has changed. Now, I believe this time that because I have such a big value of T, that this is going to become the most important piece of my problem, right? So my delta H is negative, that's a vote for. My delta S is negative, that's a vote against. But I think because we have such a big value of T, that this term, this vote against, is going to become the winning vote. So for this one, I'm expecting it to be not spontaneous, because I expect the no vote, right, because this is negative, to be the dominant one. But again, let's throw our numbers in. So let's move our delta G way over here so that way I got some room. The delta H is still a minus 15.2 kilojoules per mole. Minus. The temperature is now 500 Kelvin, so 500.0 kelvins. And my delta S is the same as it was before. It's a negative 0.173 kilojoules per Kelvin dot moles. And you can see the second time around, I may have run out a little bit of room here for my units on my delta S, but I've got my problem now centered a lot better so it's easier to see what's happening. Like, it's much easier to see that the kelvins for the temperature and the kelvins in the enthalpy change, numerator and denominator, will cancel. Right? It's a little easier to see that you're going to be left with kilojoules per mole. Right? And that's what we want. So just like the last time, let's do it in pieces. You have to do the multiplication first, so delta G equals a negative 15.2 kilojoules per mole minus. Okay, 500 times a 0.173 negative gives me a negative 86.5 kilojoules per mole. Because the Kelvin is gone, the Kelvin's gone, leaves you with just kilojoules per mole. Now you have a negative and negative, so they become pluses. And you can see this second term has really expanded, right? The second term was 1.73, and now it's like 86.5. It's definitely the bigger of the two. This is going to be the dominating term when I add them together. So if we do put them together, I've got a negative 15.2. I'm going to add on a positive 86.5, and I'm going to get 71.3 kilojoules per mole. Right? If this is kilojoules per mole, this is kilojoules per mole, this is kilojoules per mole. The only time you ever get canceling is when they're multiplying, not when they're adding. Because the delta G is positive, this reaction is now non-spontaneous. Right? At low temperatures, the delta H was the driving force, and the delta H said spontaneous, so it was spontaneous. At high temperatures, the delta S term becomes the driving force, and it said non-spontaneous. So at high temperatures, this whole thing becomes non-spontaneous. Okay, there's a change. For some reactions, at low temperatures and high temperatures, at all temperatures, it'll always be spontaneous. For some reactions, low temperatures, high temperatures, it'll always be non-spontaneous, but there are some that are going to change, right? Low temperatures, it'll be one, and at high temperatures, it'll be the other. Okay, let's talk significant figures for a minute. If you are not worried about significant figures, then the answers I've got are golden. But if you are worried about sig figs, when you are multiplying, you always use the least number of significant figures. So 500.0 has 4 significant figures. The 5, the 0, and the 0. It has 4. The negative 0.173 only has 3 sig figs. The 1, the 7, and the 3. The 0 is not significant because I didn't need to write it there for you to understand what this number was. Right? If I called it a negative 0.173, or if I called it a negative 0.173, right, the 0 really didn't need to be there. Plus, you can see that where it came from, right? Before I divided it by 1,000 to change the unit, it was 173. 173, 3 sig figs. So if this has 4 significant figures and this has 3 significant figures, then the answer should only have 3. The 8, the 6, and the 5, it only has 3. Now, when you're adding and subtracting is all about decimal places. So a negative 15.2 has 1 decimal place. 86.5 has 1 decimal place. So my answer should only have 1 decimal place. So the way I've done this problem here is already perfect. But if we move up to the A, okay, when I had 10.0, this only has 3 significant figures. 1, 2, 3. The 1, the 0, and the 0. The 173 also has 3 sig figs. The 1, the 7, and the 3. Right? 0 out in front here doesn't count. Generally, zeros in the front of a number don't count, but zeros at the back of a number does. So if you've got 3 sig figs times 3 sig figs, your answer should have 3 significant figures. The 1, the 7, and the 3 are 3 significant figures. So that's good. But when you're adding, it's all about the decimal places. This was 15.2, 1 decimal place. This is 1.73. It has 2 decimal places. So my answer should have only had 1 decimal place. So this 13.4 should get rid of the 7. It should only have 1 decimal place. Because the thing that I want to get rid of is bigger than 5, I have to round up. So if you were doing this first one with significant figures, then your answer would have been minus 13.5, right? You would have rounded the 4 up to a 5 kilojoules per mole. Okay, so for this one here, you would have to do a bit of rounding because 1 decimal place versus 2 should only have 1 at the end. Now, if you are not concerned with significant figures, leave it as a minus 13.47. That's perfect. Now, the other thing that we could ask you to do in this kind of problem, right? Because it's like, calculate delta G, is it spontaneous or not? Calculate delta G, is it spontaneous or not? Right, so we can ask you to do that a few times. But the other question is, if it's changing from spontaneous to non-spontaneous, what temperature does that happen at? Right, because low temperature is spontaneous, high temperature is non-spontaneous. There's got to be a transition temperature. So the question is, at what temperature does it become, does it transition between spontaneous and not? Now, we're going to use the exact same formula. So we're going to talk delta G equals delta H minus T delta S. I'm going to write my variables off to the side. Delta G, delta H, T, and delta S. Unlike the last two times, this time the temperature is what I'm looking for, right? I want to know what temperature does this thing transition between spontaneous and not. So if I pull back the original problem so we can steal some numbers. In the original problem, it tells me my delta H, right? The delta H was a minus 15.2 kilojoules per mole. The original problem tells me my delta S. It's a minus 173 joules per Kelvin dot mole. We had already decided kilojoules versus joules, they don't match, so we got to fix it. So we had already decided to divide this by 1,000. So that way I've got minus 0.173 kilojoules per Kelvin mole. Okay. Now, if this is the thing that we are looking for, then I need to know the value of everything else, right? You can't have more than one thing that you don't know. When we flip back to the old problems, right here are my old problems, you knew 3 and you were looking for 1. You knew 3 and you were looking for 1. So for this problem here, if I am looking for the temperature, then I have to know everything else. I have to know the delta G. Well, that's where this page comes back, right? Remember how we said delta G, when it was negative, you were spontaneous. When the delta G was positive, you were non-spontaneous. And we talked about the transition happening when your delta G is 0. When your delta G is 0, you're at equilibrium, right? You're not really spontaneous, you're not really non-spontaneous. That's the transition. So for this problem here, even though it doesn't tell you what the delta G is, when the problem talks about the transition between spontaneous and not, this is a 0 kilojoules per mole. Okay, it's a little tricky. You've got to be able to remember that and add it to the problem without being told. But once you know that, now it's just throw the numbers in and solve it. Right, my delta G is 0 kilojoules per mole. My delta H is a minus 15.2 kilojoules per mole. Minus. The temperature I don't know, so let's leave it as a T. And the delta S I do know. Make sure you use the one with the units that match. So that's a minus 0.173 kilojoules per Kelvin dot mole. Now, if we're going to solve this, we're going to have to start isolating this T, right? We need to move all of this stuff to the other side. So I need to move the 15.2 to the other side, and I need to move the negative 173 to the other side. If you're doing rearranging, you always move the thing that's been added or subtracted first. You move the thing that's been multiplied second. So I would like to take this and move it to the other side first. Now, in the world of math, positives and negatives, plus and minus, are opposites. So if this is a negative 15.2 on this side, when I move it to the other side, it should become positive. So this will be a 0 kilojoules per mole. Instead of a minus 15.2, it's going to become a plus 15.2 kilojoules per mole. Right? If you take a negative number, move it to the other side, it becomes positive. If this was positive when you moved it, it would become negative. Now what do you got left over here? See this minus sign out in front, right? It was minus 15.2 minus the t. I didn't do anything with that. That's still there, so that's a minus. The t is still there. And the minus 0.173 kilojoules per Kelvin per mole also still there. So let's add these two. 0 plus 15.2 is 15.2 kilojoules per mole. Negative out in front, there's my T, and a negative 0.173 kilojoules per Kelvin dot mole. Now, let's talk about units canceling. Actually, let's leave the units for right now. We'll cancel them in a minute. Okay, so this one was added and subtracted, so we moved it first. The one that's multiplied, we moved that second. So if you are multiplying something, the opposite of multiplying is dividing. So I'm going to divide this side by everything in this bracket. The minus, the 0.173, the kilojoules, the kelvins, and the moles. Right? If you want to get rid of it, you divide it off. And this is math. So whatever you do to the right side of the problem, you also have to do to the left. So I'm also going to divide this by a negative 0.173 kilojoules, kelvins, dot moles. And the nice thing is, if you look at the two brackets, they're identicals. So the negatives cancel, the 0.173 cancel, the kilojoules cancel, the kelvins cancel, the moles cancel, like everything cancels. The only thing that you're left with is the negative out in front and the T, right? The rest cancel. Now over here, we'll pull out our calculator. So if I've got 15.2 divided by a negative 0.173. So 0.173 negative equals. That's a negative 87.86. Now let's talk about units. Anything that shows up in both a numerator and a denominator cancels. So I got kilojoules on the numerator, and I got kilojoules down here in the denominator. I got moles here on the top. I got moles down here on the bottom, they cancel. So the only thing I got left is the kelvins. Now, it is a bit of an unusual spot because it's like this would be the numerator, this is the denominator, and it's in the denominator of the denominator. So it's like having 1 over kelvins, right? Because these are all gone, so that's like a 1. This is gone, so that's like a 1, and it's got 1 over Kelvin. So if you've got 1 over kelvins, the two denominator things, they cancel each other out. So this will be a minus 87.86 kelvins equals minus the temperature. Now, that's to be expected, right? This is a temperature, and you would expect it to be in kelvins in this problem. Now, we do have the issue where you got it as a negative temperature equals a negative 87. But in the world of math, if you've got a negative on both sides, you can just cancel them out. So the final temperature, the temperature where it's going to switch between spontaneous and not spontaneous, is 87.86 kelvins. That'll be the switchover temperature. Now, for this one here, I did decide to keep all of the units in so that you could see the canceling. If you're not required to keep the units in the calculation, if you're only required to have them at the end, let's retry the problem. Okay, so let's just cover up what I've got. If you're looking for temperature, you know that in this calculation, the temperature is going to be in kelvins. So if you know what the final answer is going to be unit-wise, and you're not required to keep the calculations as you go through, well then maybe you should just skip them as you go through. Let's try a different sheet of paper, something that doesn't have stuff written on the back. So if I just put the numbers in, your delta G is 0. Your delta H is a minus 15.2. Minus your temperature times your delta S. And your delta S is a minus 0.173. Now, if you are going to leave out your units, You do have to make sure they match, right? The matching part is important, even if you don't write the units in. If this has kilojoules, this needs kilojoules. But by leaving the units out, now it looks more like a math problem and less like a chemistry problem, right? I'm still going to move the minus 15.2 to the other side, where it will become positive. So 0 plus 15.2 equals a negative T times a minus 0.173. 0 plus 15.2 is 15.2. So that's a minus temperature times 0.173 negative. And now if these two are multiplied, you get rid of it by dividing. So divide by the negative 0.173, divide by the negative 0.173. So if we pull out our calculator again, 15.2 divided by 0.173 negative, again gives me a minus 87.86. This cancels out with this, and it leaves me with minus temperature. Right? Now it looks more like a math problem. There's less units kind of floating around. It makes it look less complicated. So if you don't have to keep the units in the calculation, drop them, right? Because you know what the unit should be. When I cancel out these two negatives and I get 87.86 equals the temperature, you know that for this formula here, the temperature is always in kelvins, so I can just throw in kelvins at the end, and I got my answer. This is the temperature where the transition happens. All right, let's talk about significant figures. If you don't have to worry about significant figures, then your life is good. But if you do, when I add these two together here, adding and subtracting is all about the least number of decimal places. This one has one decimal place. The 0 has as many decimal places as I want. Because when I say that the delta G is 0, I'm saying that it's exactly 0. So this would be like 0.0000 kilojoules per mole, right? It has as many units as I want it to have, or as many decimal places. Because it is exactly 0. So I could call this 0.0 if I wanted to, because it's exactly 0. So 1 decimal place plus 1 decimal place gives me 1 decimal place. That's good. Now, when I do the division, divisions are all about significant figures. So in 15.2, I have 1, 2, 3 significant figures. In the negative 0.173, I have 1, 2, 3 significant figures, right? Because the 0 doesn't count. So if you've got 3 sig figs divided by 3 sig figs, my answer should only have 3 significant figures. So keep the 8, keep the 7, keep the 8, get rid of the 6. Because the 6 is bigger than 5, you're going to round up. So my final answer would be 87.9 kelvins is the temperature. Now, if you don't have to worry about significant figures, just leave it as 87.86. But if you are worried about sig figs, 87.9 is the answer that you want. Okay? Now, this is a single example, right? I did the calculation at a low temperature, I did it at a high temperature, and then I found the transition temperature. To get good at these, you're going to have to do it multiple times. So my suggestion is, now that you've seen it done, restart the video, get to the point where I'm showing you the problem, and then pause it. Attempt to do the calculation yourself, and then check to see if the answer is correct. Right? The only way that you're going to get good at this is if you do practice it a few times. So I'm hoping that this has helped you with calculating delta G and determining whether a reaction is spontaneous or not. And as always, thank you for joining me here at Chemistry with Dr. Clark.